Now let's talk about one more application of aqueous equilibrium, one that doesn't involve acid-base chemistry. This is going to deal with solubility product. And so in this first video of this section, we're going to talk about the solubility product constant called Ksp, and also talk about water solubility. Now, many compounds are readily soluble in water, like sodium chloride, for instance, has a fairly high water solubility. And so we will assume that sodium chloride, when put in water, will dissociate and dissolve completely to make Na plus and chloride ion in the aqueous phase. We'll assume that it goes to completion, meaning that we'll use a one-way reaction arrow. However, there are many compounds that are not so soluble in water. Silver sulfate, for example, would be an example of a compound that's fairly insoluble in water. Now, that doesn't mean that it doesn't dissolve at all. What it means is that it dissolves to a very small extent in water. So we can still write a dissociation and dissolution reaction, but we're going to write this as an equilibrium reaction because it is possible for some of the silver sulfate to dissolve into solution to make Ag plus and sulfate, but not very much of it does. And so we establish an equilibrium, and equilibrium will very heavily favor the reactant side of this equation due to the fact that silver sulfate has a low solubility in water. Now, the way that we would describe this equilibrium would be via equilibrium constant expression, and we give a special name to this equilibrium constant expression when we're talking about the dissolution or dissociation of an ionic compound into solution. We're going to call the equilibrium constant K subscript Sp. And so that Sp stands for the solubility product. It's the equilibrium constant expression for solubility. We could go ahead and write out what the Ksp expression would be for the dissolution and dissociation of silver sulfate in an aqueous solution. And so the Ksp expression for this reaction would be Ksp is equal to, for our products, we have Ag plus, and the coefficient is 2, and so that's squared. That's important to point out here because for a lot of the reactions that we've looked at over the past several videos, everything has all been 1-to-1 mole ratios. And so we haven't had to worry about that exponent. But here in these water solubility or in these solubility equations, we'll sometimes see coefficients. So don't forget to take those into account when you're writing the Ksp expression. Our other product is SO4 2 minus. So that also is included. The coefficient is 1, so the exponent is 1. You would divide products by reactants, but on the reactant side of the equation, we have a solid, and solids don't count. So we don't need to write anything down in the denominator for this. All right, in this example, what we're going to do is calculate the water solubility of silver sulfate. And we're given what the Ksp is. We're told that it's 1.2 times 10 to the minus 5. Let's go ahead and set up the ice table to help us calculate what the water solubility will be. To accomplish this, we're going to write out the dissociation reaction. Goes to 2 Ag plus SO4 2 minus. And also, we're given what the Ksp is, but it's also helpful to write the actual Ksp expression. So I'll write the Ksp expression again here. Ag plus squared, SO4 2 minus. And then we make the ice table. Now, the amount of Ag2SO4 solid is inconsequential. It doesn't matter how much you have because Ag2SO4 is a solid and it does not appear in the Ksp expression, so it does not matter how much of this is present. We'll just cross that column out. Now, in water, you'll initially have no Ag plus and no SO4 2 minus, right? So initially, it's just pure water, nothing for the Ag plus and SO4 2 minus ions. Therefore, this process has to proceed to the right. You're going to make some Ag plus, you're going to make some SO4 2 minus. And we'll say that for Ag plus, it's 2x because the coefficient is 2. And for SO4 2 minus, it's x because the coefficient is 1. So at equilibrium, you'll have 2x as the concentration of Ag plus and x as the concentration of SO4 2 minus. These values get plugged into the Ksp expression. So we'll write that in. And what we'll have is 1.2 times 10 to the minus 5 is equal to the concentration of Ag+, which is 2x, the quantity squared, times the concentration of SO4 2-, which is just x. Don't forget that that squared has to be applied to both the x as well as the 2. It gets applied to everything inside of the parentheses, so watch out for that. So when you distribute that throughout, you get 1.2 times 10 to the minus 5 equals 4x squared times x. So 1.2 times 10 to the minus 5 is equal to 4x cubed. Therefore, you can end up saying that x cubed is equal to 1.2 times 10 to the minus 5 over 4. And to just isolate what x is, you'll have to take the cubed root of both sides. So raise both sides to the 1/3 power. And when you do that, what you'll find is x comes out to be 0.014. Now, we have to think about what this value of x means. So in this ICE table, what we're seeing is x refers to the extent of the reaction, right? It's telling you how much SO4 2- is being produced, but it also would be telling you how much of the Ag2SO4 has been consumed, right? It's telling you the extent of this reaction. How far is it traveling to the right? And so what x represents is the water solubility of this Ag2SO4. So whenever you're asked to find the solubility, what the problem is asking you to determine is, what is x in the ICE table? The value of x will always refer to the solubility when you're doing one of these KSP problems. So x is the solubility. And so what we can say is that you can dissolve 0.014 moles of Ag2SO4 in every liter of water, right? Because remember that in these ICE tables, when we're dealing with a K expression like this, we're dealing with units of concentration, right? So that's how I can assign those units, 0.014 moles per liter. So you can say that 0.014 moles of Ag2SO4 per liter will dissolve. All right, so that gives us the water solubility of Ag2SO4. And in the next video, what we're going to do is consider what would happen if instead of trying to dissolve Ag2SO4 in water, we dissolve it into a solution that contains a common ion.